Hello everyone. In this video, we are going to discuss about electrical capacitance of a body. Capacitance. It is denoted by a letter capital C. So, for example, let us consider a body. Clear? So, any random consider body. It's a neutral body, means it is uncharged. The value of Q is charged, 0. Now, we have a task, we have to charge this. So by any method, by induction or any kind of method, you are charging it. So you are charging it, so you started charging it, let it be positive charge. So you charging it. So now the charge is Q. Clear? Whenever you are charging, what about the potential of this body? So initially the charge was 0. Then the potential was also 0. The potential of this body was also 0. But later you started charging it. So the charge increases, then the potential also increases. Now there is a potential around this. Clear? There is a potential. So it is clear that the more the charge you give, the potential will be increased. So there is a relationship between the charge and potential of that body. That means they are directly proportional. Clear? If you charge it, the potential will be increased. Okay. So this is the relation between charge and potential. So now let it be capital Q. So this Q is equal to CV. Where here C is a constant, the constant of this material, and this constant is called capacitance. The constant is called capacitance, or we can say C is equal to, from this equation, let's rearrange, C is equal to Q by V. Its SI unit is farad, or you write capital F. Okay, so what is capacitance? It's a property of a material. It's a constant. Clear? That means the ability to store charge in a body. The ability to store charge in a body. That is constant for a body. Clear? So this is what we call capacitance, and denoted by C. The factors affecting capacitance of a conductor, it depends on a number of factors. The first one is the size and shape of a conductor. Second one, it depends on the capacitance of a conductor. It depends on the medium where it is kept. That means the nature of the medium. Nature of the medium means the permittivity of that medium. Okay. And the third factor is the presence of other conductor in the neighborhood. If you keep a neighborhood, in the neighborhood, if you keep some other conductor, then the capacitance, the ability to store the charge of the first conductor may vary. So these are the factors affecting capacitance of a conductor.
Our next topic is capacitor. A capacitor is an insulated conductor which is used to store electric charge or electric energy. These pictures are different types of capacitors. The symbolic representation of capacitor is given. The first one, A, it is a fixed capacitor. It means its capacitance is fixed. Look at the second one, B. It's a variable capacitance. You can change, you can vary its capacitance.
Now, the principle of a capacitor, the principle of working of a capacitor. Okay, so we have a conductor here, we have a plate. it is initially it is neutral. Clear? It has its charge is 0. Okay, it's plate number 1. Now we are going to charge it. We have to charge it. Clear? Whatever charge is possible, that much charge you have to add it to it. Clear? Because this body, if this conductor, every conductor has a contact, it's an ability to store charge. It's called its capacitance. Okay, so now at present it has a capacitance. So anyway, so I'm considering its capacitance. Let it be C1. Let it be C1. Now I'm charging it. I'm charging. So let it be positive charge. So I charge it. Now its charge, the stored charge is Q. So when the charge was increased, we know charge and potential, they are directly proportional. When the charge increases, the potential will also be increased. So now at present, it has a potential, it's V. Now this is positive potential V. Okay. Now, it is completely filled with the charge. It has got the saturation, we can say. Now, we have to add more charges. We have to charge it further more. Clear? But the capacitance is completely filled. Now it's not possible. Let us see, is there any other way to charge it? So we know there are three factors affecting capacitance. What are they? The first one is the size and shape. But this is the size and shape. Anyway, we are not allowed to change the size and shape. So that is not possible. Now the second factor is the nature of the medium, surrounding medium. So medium right now we imagine it's vacuum, it's space. Okay, so that is also we are not allowed to change it. Now, is there any other method to increase its capacitance? Because we need to add more charges into it. Now, what is the third factor affecting capacitance? Yes, the presence of another conductor. Yes, this is a possibility. So now let us bring one more conductor. So let's consider the similar one, exactly the same. We are bringing one more conductor of the same size or the same shape. So then, now, but it is neutral, it's uncharged. Okay, I brought it and I placed it here. Now see here, before I brought here, this plate number 2, this conductor was uncharged, but it is a conductor. Now it is placed in the electric field of the first one. Why there is a field? Because now first one is already charged. So there is a field around it. When I place this second plate in the field of first one, there will be electrostatic induction. And do you know what will happen? Near the positive side, some negative charges will be induced. And what will, similarly on the other side, an equal positive charge will be produced. Okay. Due to electrostatic induction. Now, due to this minus charges in the left hand side, there will be a negative potential, and on the other side there will be a positive potential. Now, listen carefully. Both the potential, negative and the positive, it will affect this potential of the first one. The presence of negative will try to reduce this potential, and the presence of this positive will try to increase this potential. Both will affect. But do you know which side, the negative or the positive, which is more close to plate number 1? Yes, it's a negative. So the effect of negative potential will be more effective. It will be more effective. So you know what happened? Clear, it will be more. So this potential will be slightly decreased. So this potential will be decreased. Remember, if the potential is decreased means you can add more charge. That means its capacity, its capacitance has increased. So now let's consider its capacitance has slightly increased to a new value. Let it be C2. So what was the reason? Because the presence of this second plate. Okay, got it, good. Now I'm charging it. I'm charging, so furthermore I can charge it more, so because the capacitance has increased, so I charge it. Furthermore I charge it. So when I'm charging it, that effect will be on the other side also. Clear, here also the same effect will be there, because this will get more induced, electrostatic induction will be there. So anyway, again, finally it has come to the same potential again, the previous same potential, but ultimately the capacitance has slightly increased. Now, listen carefully. This positive side of the plate 2 am earthing. We know Earth is a universal acceptor of charges as well as the donor of charges. Now look at this. The positive side is connected to the Earth. That means Earth will provide electrons. So you can see that the electrons will flow from the Earth to this positive side, and do you know all this positive will be neutralized. So that means no more positive here. So it has completely neutralized. That means no more potential, positive potential. So that positive potential, it has slightly increased this potential, but right now that positive is not there. It is gone due to earthing. Clear? So what will happen? This will be slightly reduced again. That means you can add more charges, further more charges. That means its capacitance has further increased to another value. Clear? So this is the presence of, this is how the presence of a conductor affects the capacitance of a conductor. So it's better to have two plates to store more charges. Clear? So the next topic is parallel plate capacitor. That means there are different types of capacitor, but most commonly found capacitor, you can see that means parallel plate capacitor, which store a large amount of charges than a single conductor. Now, the combination of capacitors. Capacitors can be connected in a circuit, electronic circuit, in series or parallel. So let's start with the series. So here we have three capacitors. So this is the first one. It has a capacitance C1, and this is C2, and this is C3. And all these capacitors, they are connected to a cell of potential difference V. So this positive and negative. So when you connect this, you know what will happen? The current will flow from positive to the negative. So it's clear that all the roads, all the plates where the positive is connected will be positively charged. And here on the other side it will be negatively charged. And all these are connected in series. So remember, when they are connected in series, we have studied in lower classes, the current which is passing through all these terminals will be the same. Clear? It will be the same. That means whatever their capacitance, it is maybe same or maybe different. At present they are different. That's why we have taken C1, C2, C3 separately. The charge stored on them will be same. Clear? The same charge will be stored. So here the charge stored is Q. It will also be Q. It will also be Q. Clear? But the potential difference across each and every capacitor will be different. So across the first capacitor, the terminals of the first capacitor C1, the potential across these 2 points will be V1, and between the second capacitor C2, it will be V2, and across the third capacitor will be V3. And it is clear that the sum of all these potential difference across the capacitors, across the plate terminals of the capacitor, that is V1 plus V2 plus V3, will be the applied potential difference of the cell, that is this V. Okay, now we know that we have the basic equation, the capacitance C is equal to Q by V. what will be V? V is equal to, it will be Q by C. So what will be the potential difference of the first across the first capacitor? So that is V1 is equal to Q by C1. I am not writing Q1 because all the capacitors, they have the same charge Q. Similarly, what will be V2? It will be Q by C2. What about V3? It will be Q by C3. Okay. Now, what will be the applied potential? V is equal to, that is also Q divided by CS, where CS means the total equivalent capacitance of this system. The system of three capacitors which are connected in series. Clear? That is CS. Now let us substitute all these values V1, V2, V3 and V in this equation. So what will happen? So that is, this will be equal to, or okay, let's substitute this one. V it is Q divided by CS is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3. So in the RHS you can see Q is common, so I can take Q common outside, so it becomes 1 by C1 plus 1 by C2 plus 1 by C3. So this Q and this Q will be cancelled, and finally you will get 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If there are more capacitors, and it will continue. So this equation will give you the net capacity, the total equivalent capacitance of capacitors. They are connected in series. Next is the parallel combination. So look at this. We have three capacitors. So this one is C1, C2, C3. All of them are connected in parallel, and it is connected to a cell of potential V. So it's positive and negative. In parallel combination, we know that, the potential difference across all the capacitors will be same. So that means the first one, it will also be V, second one will also be V, third one will also be V, and that will be same as the cell. Okay, but when the current is going from the positive terminal to the negative terminal, it will split at this junction. That means the current will divide according to its capacity. Clear? So in this case, when they are connected in series, the charge stored will be different. So here the charge stored, here's this, all this side will be positively charged, this side will be negatively charged. So this, the first capacitor will store a charge Q1, the second one will store a charge Q2, and the third one will store a charge Q3. Clear? And the net charge stored in this system of capacitor which are connected in parallel will be Q is equal to Q1 plus Q2 plus Q3. Okay. Now we know the capacitance C is equal to Q by V. Then what will be Q? When you rearrange this, Q is equal to CV. So what will be the value of Q1 here? So that Q1 will be C1 V, not V1, because see, all of them are in parallel, so the potential difference will be same across all the capacitors. Similarly, what will be Q2? Q2 is equal to C2V, and what will be Q3? Q3 is equal to C3V, and what will be the net charge stored? That will be CPV. The CP is the net equivalent capacitance of the system of capacitors. So let us substitute all the values Q1, Q2, Q3 and Q in the first equation. So that will become, it is CPV is equal to C1V plus C2V plus C3V. So V is common here, so that is CPV is equal to C1. Let's take the common outside. V, it is C1 plus C2 plus C3. So you can cancel on both the sides. So that's finally the net effective equivalent capacitance CP is equal to C1 plus C2 plus C3. So this will give you the equivalent capacitance of a system of capacitors. They are connected in parallel. Now it is clear that from both the equations, that means the effective capacitance in series and parallel, it is clear that in series combination the net capacitance, the equivalent capacitance decreases even less than the individual capacitance of individual capacitors. But in parallel combination, the net capacitance is increasing